Ever wonder how an AI can understand a really complex sentence, but can also, just spot a cat in a photo? Well, the secret is that they use two totally different kinds of digital brains. Today, we are going to break down the huge difference between feedforward and recurrent neural networks. So let's get right into it.
Okay, so right off the bat, you can see the core difference just by looking at them. Over on the left, you've got the feedforward network, the FFNN. See how it's just a straight shot? Information goes in one end and comes out the other. But then look at the recurrent neural network on the right, the RNN. It's got loops. Information can actually circle back on itself. And that one little design change, it changes everything.
All right, first up, let's talk about how information actually moves through these things. Honestly, this is the most crucial distinction between them. Think of an FFNN like a one-way street. Data gets in, it gets processed layer by layer, and then it exits. That's it. It never looks back. An RNN, though, that's a different story. It's more like a city full of roundabouts. The connections actually form cycles, so the network can feed its own output back into itself. And that feedback loop, that's the secret sauce.
So what's the big deal with that feedback loop? Well, it gives the recurrent neural network a superpower that the feedforward network just doesn't have. And that superpower is memory. You see, this difference in data flow has a massive consequence. An FFN has, for all intents and purposes, total amnesia. Every time it sees a new piece of data, it's like it's seeing something for the very first time. It has zero memory of what came before. But an RNN? Oh, it remembers. It uses something called its internal hidden state to keep a running tally of past information. And this quote really just hits the nail on the head. For an RNN, the past directly, and I mean directly, shapes the present. So when it's trying to predict, say, the next word in a sentence, it isn't just looking at the word it's on right now. No way. It's considering all the words that came before it. For an RNN, context is king. So, all this talk about architecture, it all boils down to one really practical question. When do you actually use which network? And the answer, as it turns out, depends completely on what kind of data you're dealing with.
FNNs are the absolute masters of what we call static data. And what's that? It's basically any information where the order doesn't matter one bit. Think about a single photograph, or a list of numbers for a loan application. The sequence of that information is totally irrelevant to the final decision.
And that's exactly why they're perfect for jobs like image classification. Is this picture a cat or a dog? Or for object detection, like finding all the cars in a photo. Each one of those is a self-contained problem. It's completely independent of whatever came before or after it.
Now, on the flip side, we've got RNNs. These are custom-built for sequential data, where the order is literally everything. I mean, think about it. The phrase dog bites man means something completely different than man bites dog, right? The meaning is locked inside the sequence.
And this is where RNNs truly shine. They're the brains behind stuff like speech recognition, where the sound that came just a moment ago helps predict the next one. They're used for sentiment analysis, like, is this movie review good or bad? You have to read the whole thing in order to find out. And of course, time series stuff, like trying to predict stock prices.
Okay, so this memory superpower sounds amazing, right? But it isn't free. As with pretty much everything in computing, with great power comes great complexity, and yep, a much bigger computational bill.
An FFNN is pretty straightforward. It's just simpler, and that makes it a whole lot faster to train. An RNN, with all those looping dependencies on time, is just a more complex beast. Training it means you basically have to unroll all those loops through time, and that process is much, much slower and needs a lot more horsepower.
And that complexity leads to some pretty unique headaches. The most famous one is called the vanishing gradient problem. It's actually a great name. In simple terms, think of it like this. The further back in a long sentence an RNN has to look to find context, the weaker its memory gets. The signal it needs to learn from something way back at the beginning can get so faint, so quiet, that it basically vanishes.
All right, let's just pull all this together for a quick summary. For data flow, FFNNs are a one-way street. RNNs are cyclic with those loops. For memory, FFNNs have none. RNNs use hidden states to remember. So FFNNs are best for static things like images, while RNNs are perfect for sequential stuff like text. And the big trade-off? FFNNs are simpler and faster, but RNNs are way more complex, slower to train, and can get tripped up by problems like those vanishing gradients.
And that leaves us with a really fascinating final thought. We've seen that RNNs have this amazing memory.
but we also know it can be flawed, that it can fade over long stretches. So the big question becomes, if a network's memory can just fade away, how in the world do we build machines that can truly learn from the deep, deep past? Well, that's a story that leads to some even cooler technology.